Hello and welcome to our class on exobiology. And here we're going to start lecture 2 on the birth of planets, stars, and the formation of the heavy elements. And just as a reminder, this is the second lecture in the UBO Libre exobiology from the Big Bang to the appearance of life here on Earth. And I'm your lecturer, Rob Scott, teaching the astrophysics part of this class. And how is this birth of planets and stars related to exobiology? Well, exobiology, remember the primary question we're asking is, does life exist beyond planet Earth, or has it ever existed? So to approach this like scientists, we first think, well, you need, first of all, a place, a shelter where you can develop life. Now already we have a problem because we don't know the constraints on what this shelter should look like. What properties does it need? So in the spirit of being conservative or cautious, let's look for a place that's a little bit like planet Earth. So a rocky planet where we have water in the liquid state, and we have the elements that are essential for life, at least life as we know it here on Earth. So these are the elements, the schnapps. So that's an acronym for carbon, hydrogen, nitrogen, oxygen, phosphor, and sulfur. And I think all that's obvious to a francophone with the possible exception of the nitrogen, N is nitrogen, which is azote en français. So our interest then is, are there lots of these planets like the planet Earth? And if they do exist, how long do they exist? So notice we've reduced our problem at least to a first question in astrophysics, as astrophysicists would like to do. And so how can we address this astrophysical question in a scientific fashion? How many Earth-like planets are there elsewhere? Well, we could, of course, we want to be scientists, so we could just look in the universe around us and look for these exoplanets. I'm going to call them exoplanets. Planets, that means planets outside of the solar system. And our capabilities allow us currently to look in our sort of immediate neighborhood here in the Milky Way galaxy. So of course this is a good idea, but it's a good idea because science is an empirical activity. And I've noticed my colleagues love to remind young students about this. So I found on the internet an example of the chemist Michael McBride. He spends 20 minutes underlying the point that experiments are important for chemistry. And here's the YouTube link. But I think you all know that, right? If you've been paying attention, you're living in the 21st century. I think this is has become painfully obvious. I think what's a little less obvious and worth emphasizing is the following point. Well, the point is that observations alone are not enough. So imagine that we do this. We use our very sensitive astronomical techniques for observing around us, and we discover exoplanets. In fact, since the last few decades, we've done exactly that, and we've discovered more than 4 million exoplanets within 2,000 light years of our solar system. So that's exciting. That gives proof of the existence of these exoplanets in our neighborhood. But there's only a few thousand of them. How do we know that they exist even further? Unfortunately, our methods are too weak to find them at further distances. So how could we know that there are even more exoplanets? Well, alternatively, we should do the following. We should try and understand, where does the Earth come from? Where do the heavy elements come from? Heavy in this context means with atomic number bigger than 2. Where does the sun come from? How old are the planets and the sun and the solar system? And how long will they last? With this knowledge, then we're better placed to address this question of the number of places, shelters, if you like, where life might develop, at least Earth-like shelters beyond the solar system. So I guess the point I'm making is that experiments and observations, of course, they're important for science, but they're important because they verify our models and our theories. And this allows us to understand the observations and then to go beyond those observations. So that's why we're going to go into all this theory. Okay, so what is a star? Well, we can go back to René Descartes, because we're here in France. And so Descartes, already in the 17th century, realized that stars might be just like suns, only much further away. In other words, he realized that our sun might be a star, it's just that we're close to it. But to verify that idea, we needed to wait until the 19th century. We had to wait for improvements in techniques of astronomy. So what were those developments? Well, in fact, they developed the method of parallax. It's the same word in French. And by that, I'll try and explain it very roughly, and then we'll watch a little video which can explain it with diagrams and animations better than I can. But basically the idea is that it's a geometrical effect, knowing the size of the Earth's orbit about the sun in a year. So the Earth-Sun distance is 1 astronomical unit by definition, which is approximately 150 million kilometers. That's the radius of this near circular orbit of the Earth about the Sun. Knowing this distance and the apparent movement of this star that's not too far from us during this 6-year period, so that apparent movement of the star is with respect to the stars that are much, much further and therefore appear fixed. And using a bit of geometry, this elementary Euclidean geometry that you learned in lycée, you can calculate the distance between our sun and the this star that's not too far from us. So I'm going to now follow this link, which we followed this link here, which you'll find in the course notes. And so I'm going to play that for you now, or you can play it on your own.
La parallaxe permet de calculer la distance d'une étoile proche. À un moment donné, l'étoile occupe une certaine position dans le ciel qui détermine une ligne de visée. 6 mois plus tard, la Terre est à l'opposé sur son orbite. L'étoile semble avoir changé de position par rapport aux étoiles lointaines immobiles. On détermine l'angle entre les deux lignes de visée. Il suffit alors de tracer un triangle rectangle entre la Terre, le Soleil et cette étoile. On connaît la parallaxe P, qui est la moitié de l'angle observé. On connaît également la longueur du segment A, qui est la distance Terre-Soleil. Une simple relation de trigonométrie nous dit que tangente de P est égale à A sur D. La parallaxe étant très petite, la tangente de P équivaut à P. La distance de cette étoile est donc égale à la distance Terre-Soleil divisée par la parallaxe.